Hello, how are you doing? It's Mike here, and in this video I just want to discuss a brief overview of polar equations and their graphs. The only reason why I like to focus on this is because I know many of us that have worked through algebra consistently for years have recognized there's really just one way to write one specific graph. But when it comes to polar equations and their graphs, there could be multiple ways to write an equation for the same graph. So I always like to go through this and be very cognizant of how to look at some of these and how to recognize that they can be different and they can be the same. So the first thing that I like to go through is that I like to recognize a circle, because we're going to be working with a lot of circles in our polar equations. And this specifically can have more than one polar equation. And let's look at the example of r equals to 2 and r equals to -2. So these are both the equations for a circle of radius 2, centered at the origin. Centered at the origin or the pole. So I shouldn't really say origin, I should say the pole. So centered at the poles. So just be very cognizant of that that this is the equation for a circle of radius 2 centered at the pole. It does not matter if you go -2 or +2. It is irrelevant. It is irrelevant. As theta increases or decreases, we recognize as we draw this. So as we draw this, r equals to 2, then no matter what theta is, theta could be pi over 2, 3 pi's over 2, we recognize that we're always going to have a value of +2. So very similarly, if r equals to -2, so if I were to just do a t-chart of r and theta, so -2 is always the value for r, and theta would be equal to a value of pi. So if we look at the value of pi, so pi is going to be all the way over here. And if we go a value of -2, we're actually going to be going back here to that point. Because remember, if we have a negative radius, we go to the extension of the terminal side, not the terminal side itself. So here, we're just going to be working with the exact same radius. And that's the reason why we can have a circle written by several different ways. But if we're going to write the equation of a circle in a polar form, it is just simply that value r equals to 2 and r equals to -2. We will learn how this can be off-shifted from the pole, but for right now, let's just work with something relatively easy and nothing too difficult. So now let's go ahead and try some more examples. So let's go ahead and see what happens if we're just given a value of theta. So in the form of an equation, and this is going to be a polar equation, if given a value of theta with no value of r, this is just a linear curve. This is just a linear curve. So let's look at the example of theta equaling to pi over 6. Theta equaling to pi over 6. So if we were to look at theta being equal to pi over 6, we recognize that pi over 6 is approximately, we'll just say right here, pi over 6. So that means that the line will be this guy. Try my best to draw it. Let's see if I can get it right on point. There we go. I think that's the best that I can do. So that means that we're going to have that line. So keep in mind that this is not the only way that we could write this value, this line right here. So this, as we said, from this value right here from the initial ray to the value pi over 6 can also be written in a different form. We could also write this as an extension of pi over 6 plus pi. So if we were to travel another value of pi, we could write this line as theta equals to 7 pi over 6, because pi is really going to be equal to a value of 6 pi's over 6. So 6 pi's over 6 plus pi over 6 gives us a value of 7 pi's over 6. That could also be a way that we could write this line. We could write this in a negative fashion. We could write this in a negative fashion. So maybe take a second just to pause the video and then see if you can figure out how to write this line in terms of a negative angle, any negative angle. Okay, so let's think about this. We recognize if we want to travel from here to here, that's still going to be a value of pi. That's still going to be a value of pi, which is 6 pi's over 6. But if we want to write this, we're going to have to subtract off a value of pi over 6. So we could also write this as theta equaling to negative 5 pi's over 6. Negative 5 pi's over 6. Because remember, negative 5 pi over 6 will start, and I'll do this in green. Let me do it in green so you can see it. Negative 5 pi over 6 starts at that initial ray, and we travel to that value of the line. So there are lots of different ways that we can go about defining these segments and these values. So just keep that in mind, that there's so many ways of doing it, not just one unilateral way, but the most basic of all our polar equations are those of circles and those of lines. So if we write a circle, it's going to be in the form of r equals to something. If it's going to be a line, it's going to be in the form of theta equaling something. So let's see what happens if we want to graph, and these are baby graphs. I guess these are just baby graphs. These are nothing as large as we're really going to get into. We'll do that later on. Let's say, for example, we want to look at the potential curve of 1, which is less than or equal to our value of r, which is less than or equal to a value of 2. And we want to describe this from 0 is less than or equal to theta, which is less than or equal to pi. So let's go ahead. I'm just going to put in my, oops, that's too big. Okay, so let's see what's going on here. So we have two constraints in this circumstance. 1, which is less than r, which is less than 2. So we recognize that we're working between this value of 1 and this value of 2. And here we have the restriction between 0 and pi. 0 is right here, and pi is all the way out here. Therefore, this graph is going to look something like this. So, and this is shaded in such a fashion. So here we sort of have a semicircle tire. So it's not extending over the entire curve, but it's restricted. So this is an example of how we would graph a polar set of polar points, polar coordinates that satisfy those conditions. So every single one of them would fall into that restriction. So let's go ahead and look at another example. Let's go ahead and try some other easy graphs. So let's look at another example. Let us look at -4 is less than or equal to r, which is less than or equal to 3. And we just have the angle of theta equaling to pi's over 4. So in this circumstance, a little bit too big. So let's think about this. Theta equals to pi over 4. Pi over 4 is approximately right here. So I'm just going to put this line, hopefully going right through the pole. Sometimes it goes through, sometimes it doesn't. So I seem to have no luck going right through the pole, so we're just going to have to assume it gets there as close as possible. So I'll just make this circle a bit easier. So now, if I know that the radius is restricted, or the radial value is restricted between -4 and 3, I recognize here that I have to restrict the line. And the line cannot extend all the way out. But the question is, where do we look first, or where do I restrict first? So this value is I guess the small value. This value is the large value. So I know that I can go out 1, 2, 3, 3 here. So this is my value of r equaling to 3 at pi over 4. But then it also is restricted on the negative end at -4. So I go out 1, 2, 3, 4. Everything else after this has to go away. So this is actually just a line segment, because this will give me the value of pi over 4, vi over 4 comma 3, and this is going to be the value of pi over 4 comma negative 4. Vi over 4, oh sorry, I did this, oh I wrote these backwards, I'm sorry. I wrote these backwards, so be careful, don't do that. So this is going to be 3 comma pi over 4, and this is going to be negative 4 comma pi over 4. So it's negative because my angle starts here and goes until pi over 4. Negative because we are going to the extension of the terminal side, so we're going out here. And all the points that exist between negative 4 and positive 3 along the line pi over 4 will be included. So that's how we have a line segment, for example. So there's so many different ways that we can do things that we really couldn't, that wouldn't be as easy maybe using a Cartesian plane. So let's try another example. These are sort of fun, I think. So let's look at the example. Let's look at 2 pi's over 3 are less than or equal to theta, and this is less than or equal to, let's say, 5 pi's over 6. So the question is, how do we draw something like this? So again, this is going to be some shaded in regions. So we have to figure out where are we first, and that's not so bad to figure out. So first of all, if it helps you, if it appeases your modern sensibilities, we recognize 2 pi over 3 is 120 degrees and 5 pi over 6 is 150 degrees. So hopefully we're recognizing here that we are restricted. Theta must exist between, this is basically saying theta must exist between 2 pi over 3 and 5 pi over 6. So this is the smaller value. It must be less than larger value. So this is sort of counterintuitive to our graph, but we recognize here that this and this creates our boundaries. And we're going to include every single point radius that falls in there. But however, remember, we can have radii being values that are positive and negative. So that also means that we have to include those values that fall in this quadrant. So they're also going to fall over here. So these are going to be all values that exist between 2 pi over 3 and 5 pi over 6, regardless of the length of r. So let's go ahead and change this up ever so slightly. And we go back to our, let me just grab this graph here. Let's say that we want to look at, again 2 pi's over 3, but this is less than theta, and this is less than or equal to, let's say this is equal to 5, or what did we say before? I think we said 5 pi's over 6, that's right. It's my memory going. So if we look at this guy, notice the only difference here is that we have a less than versus a less than or equal to, so it can't actually exist at 2 pi over 3. So at 2 pi over 3, we're going to have a dotted line, and that also must extend to the extension of the terminal side. And 5 pi over 6, well actually let's just make this consistent. Let's say this is less than 5 pi over 6, so we would have a dotted line along 5 pi's over 6 and 11 pi's over 6, and we would shade in everything there else. So these are sort of the inequalities that we saw when we were graphing linear inequalities and compound inequalities on the xy axis. But that's how we can actually use these to graph some basic graphs. I find these sort of fun, a little bit more exciting than doing some linear graphing, but you can really get some very interesting relationships and some very interesting graphs with something that is nothing too complex.